Um, this is about Apache Spark performance improvements. So Spark came up with multiple performance improvement when it released Spark 2.0. We're going to look at one of the blog posts that talk about it. This one is about Project Tungsten. This is one of the major improvement that Spark had with the release of 2.0 X. So what Tungsten did was the whole execution engine that Spark was using that completely got a lot of improvements. There was memory efficiency, CPU usage efficiency. Those were the main things. How Tungsten got its idea was that it looked at the modern compilers that use MPP technologies. So there are many other Apache projects that did that: Apache Drill, Presto, Apache Arrow. So Spark used all that learning from those MPP libraries and then built that into Spark 2.x. So what was done? So to reduce the JVM object memory size, creation and garbage collection processing, Spark explicitly managed the memory and converts most of the operations directly to against binary data. So essentially what we want to do here is JVM's object memory size, we want to reduce that. We want to reduce too many object creations. We want to make sure the garbage collection processing happens correctly. So what Spark did was it managed the memory and converts most of the operations to operate directly against the binary data. The next thing it did was it used a columnar layout. So instead of using a row layout, it started using a columnar layout that avoided a lot of unnecessary I/O. So what that means is the whole column A was stored together, the whole column B was stored together, the whole column C was stored together. Earlier, Spark used to store them as rows. So you'll have A, B, and C of row 1 together, A, B, and C of row 2 together, A, B, and C of row 3 together, and so on. But then the columnar layout, where it stored all the column values together, especially because all these have the same data type and follow the same compression logic, and they also help in aggregation. So when we want to do an average of this column or a sum of this column, because all the values are together, it's easy to be able to pick up and worked upon for aggregation. The next thing that happened is vectorization was done. So vectorization, what it helps is it allows the CPU to operate on vectors. So instead of operating on like multiple rows, like CPU could actually pull a whole vector and then act upon it. So which arrays, what are vectors? Vectors are actually arrays of column values. So this column, this whole thing, like 101, 102, 105, 104, 105, this whole thing got vectorized into one vector. So it's an array of one vector. So what happened is the CPU was able to process all this together, and this bottom array, 108, 112, and 114, that was another vector. It processed that separate, that batch together. So instead of processing row by row, it was able to process vector by vector. So the modern CPU designs are able to do this. So to make use of that, Spark also changed its operating methodology to actually use vectors. To improve the speed of data processing, like using L1, L2, L3 CPU caches. So there are multiple caches. They called L1 cache, L2 cache, and L3 cache within the CPU. To improve the speed of data processing, like Spark and made its algorithms and data structures use the memory hierarchy with cache-aware computations. So, like within the programs that you write, internally Spark makes it cache aware. So it understands which of the um, data is cached in what kind of cache. Is it an L1 cache, L2 cache, or L3 cache? So it understands that and then processes it. The next one is Spark SQL's Catalyst Optimizer, which is a part of um, like the optimizer here in the picture here. So Catalyst and Optimizer underpins the major new APIs in Spark 2.0 and later versions. So if you like if you're using old Sparks with RDDs, now data frames and data sets were introduced or have been introduced, and that helped with the performance as well. The Catalyst Optimizer handles analysis, logic optimization, physical planning, and code generation to compile parts of the query to Java bytecode. So any PySpark code you write, any Scala code you write, gets compiled into Java bytecode. So this Catalyst Optimizer handles the logical optimization of it, physical planning of how the query should be executed, and the code generation. So all that is taken care by the Catalyst Optimizer. The Catalyst now supports both rule-based and cost-based optimization. So it not only can do it rule-based, but also can do it cost-based. The next one is Spark SQL whole stage Java code generation. It optimizes the CPU by generating a single optimized function in bytecode for the set of operators in SQL query. So if we look at that, the whole stage code gen, it scans the JSON, filters the number of outputs, and then project them, and then collects the limit. So now that we know Spark has done a lot of improvement, how do you actually use it in your code? This is the most important piece from an application standpoint. So let's look at that. What you're supposed to do? You're supposed to use data sets, data frames, Spark SQL rather than using RDDs. So RDDs sometimes like RDDs are where you might have got introduced to Spark. So the first programs you might have learned have been through might have been through RDDs. But when you write like performance like programs that need to perform very well, rather than using RDDs, rather use datasets, data frames, and Spark SQLs. I believe data frames are supported by PySpark, and Spark SQL is supported by PySpark, but dataset is not yet supported by PySpark. But if you're using Scala, you can use dataset, data frames, and Spark SQL. So what are the advantages of actually using datasets, data frames, and Spark SQL? They allow compact columnar memory format. So in RDDs, we can't, those are not columnar format, those are row-based formats. So that does not help with compaction, and it does not help with columnar processing. You also get direct memory access. You also are reducing the garbage collection processing overhead. The Catalyst query optimization that we spoke about gets utilized, and there's also a whole stage code generation. That means it doesn't generate code by each stage. Say if there are 10 different processing steps that you write, and we actually write, it waits until the last time when you actually write to a file before it does all the other processing. So it generates the code as a whole stage instead of thinking about step one, create a code for that, and step two, and then create a Java bytecode for that, and step three, and then create a Java bytecode for that. Instead, it looks at the whole stage code, and then it generates code for that. And sometimes we are used to writing our own functions called UDFs, and it's better to avoid that because if you write your own UDF, Spark doesn't know how to exploit the parallelism advantages. So try to use the existing Spark SQL function. So Spark SQL has a lot of functions, like if you want to convert a string to date, you can use the to date function. If you want to get the R from a timestamp, you can use the R function. There are many other Spark SQL functions that are typically available in SQL and C SQL. So use those and try to avoid the custom UDFs as much as possible. That's another thing you can think about. Datasets also provide advantage of compile time safety over data frames. So again, I believe PySpark does not have this. So if you're using PySpark, you probably can ignore this. But if you're using Scala, it is even more advantageous to use a dataset over a data frame. And the advantage of that is that we get compile time safety. That means if there are any errors in the data structure, if you're trying to uh, like average a string type, then you'll get a compile time error rather than waiting for runtime to get a runtime error. So this would throw compile time error much sooner. However, like if you want to do any functional transformation like map, functional transformation like map will not take advantage of query optimization, or it will not take care of whole stage code generation and reduced uh, garbage collection. So given that, we also know that we use a lot of CSV files, but that's another thing where you can optimize your Spark programs. So Spark several supports like CSV, JSON, Orc, Parquet. Uh, like I believe it supports Avro as well. It has several data sources, including like you can go through SQL, like Oracle or Postgres. There are many connectors. You can connect to popular NoSQL databases, including DynamoDB, Redis, and you can also like use distributed messaging stores. But certain things are much faster than others. So let's look at that. But just because Spark supports all this does not mean you will get the same performance in all of them. Typically, you will have multiple data sources. So you'll have multiple sources, multiple syncs. You'll have to read a CSV file, a JSON file. You'll have to read multiple different varieties of formats. So, but when you consider read latency requirements, think about these things. So field data stores, if you're using file data stores, like anything that happens with a file, it's good for write once, read many use cases. That is, you don't do too many updates, or you don't worry about updating something. You write once and then you read many times. You don't uh, go there and update those values. So in those kind of times, the file data stores are good. So like if you're using CSV, JSON as an output, as a sync, they are good. Um, they are slower for reading. These candidates are good candidates for collecting raw data. Like if you're getting logs in a CSV, in a like space separated or a pipeline delimited format, or a comma delimited format, you can use those as like source for collecting raw data. And you can also do high throughput writes. Parquet is slow for writing but gives the best performance for reading. So if you want to write to a sync, and you want to think if you have a lot of queries that you run for reading, then Parquet is a very good option. Use that, especially if you're doing BI analytics, and it wants like you need to read it at very low latency, that you need to read quickly. So Parquet is a very good example, like option for using it as a sync. That is the target. So let's think about Apache HBase MapR database. So those are good for random read write use cases. So if you suddenly have to like read the 100th record, then you want to update the like uh, like 1 millionth record. So you want to do a random read write. Apache HBase or MapR database. Those are good options. MapR supports consistent, predictable, high throughput, fast reads and writes, and efficient updates. It also has automatic partitioning and sorting. What about Kafka? So Kafka or MapR Event Store for Kafka are good for scalable reading and writing of real-time data. MapR Event Store is good for data pipelines with stream-first architecture patterns and Kappa or Lambda architectures. So if you look at this, so we get a lot of batch sources, streaming sources, and then we process the files through like ETL. We process them through Spark, and then we store them into a HBase or a MapR database. Then we can do random read write update access. For streaming sources, we can use Spark streaming and write that to the same HBase or MapR database, and then those can be used by BI applications, batch analytics, ML analytics. So all those things can be used. So let's talk about the next thing, CSV and JSON tips and best practices. So if you're using CSV files or JSON files, while persisting and compressing CSV files and JSON files, just make sure they are splittable, they give high speeds, and yield a reasonable compression. Zip compression is not splittable. So if you have a zip compression, you cannot split the file. But if you look at Snappy, it's splittable. Snappy also gives a reasonable compression with high speed. So you get a high speed compression, but it's the compression is a reasonable size. While reading CSV and JSON files, you'll get better performance by specifying the schema. So if you're able to specify the schema and read it as a data frame, in RDDs you cannot really specify a schema, but if you're able to specify a schema and then read it using a data frame, that would give much better performance. So if you use inference, that means it has to read the first record, understand what the schema is, and then infer the schema from that, and then use it to actually process the data frame. That would be much slower compared to specifying the schema earlier and then reading the JSON file or the CSV file. It also reduces the data type errors, and obviously recommended for production code. Okay, you're using Parquet. What are the best tips and tricks that you need to use? Parquet is a columnar format. It gives the fastest read performance with Spark. So Parquet with Spark is a really good idea, especially when you're writing out as a sync and then you're using that to do multiple read operations. Parquet arranges data in columns, so it's a columnar data format. It puts related values in close proximity. So if you look at this picture, all the A's are together, all the B's are together, all the C's are together. So they put that in close proximity so that it optimizes the query performance. It minimizes the IO. It does not, and then it facilitates compression because like all the string values are together, all the date values are together, and the integer values are together. That makes like compression much easier. Parquet also detects and encodes same or similar data using a technique that conserves resources. So Parquet has an ability to encode similar data. Parquet also stores column metadata and statistics. So it can store the column related metadata, including the highest value, the lowest value, the means. So that helps Spark like process the data much faster. So if the highest, if you're querying by some number and it's out of the range of the highest and the lowest values, Parquet would immediately get back zero result. So that metadata helps, and the metadata and the statistics helps it do the query faster. Spark also has a vectorized Parquet reader. So this helps in reading multiple records together. So the multiple records, say rows 1 to 6, maybe in one array, and that is passed as a vector for processing in the CPU. So that helps doing the batches much faster. So here we talk about 10x faster reading performance. Parquet files are immutable, so you cannot actually update or change a Parquet file. So if you want to read a Parquet file and write it out into a new Parquet file, that's what you would do. So it's actually a rewrite of the dataset. For streaming data, you can stream fast read write, uh, stream to a fast read write data store. So you could write to a HBase database or to a Redshift database, and then you can extract the data to a Parquet file. If you have any analytical use case that you need to do some analysis with the stream data, then you can actually write it to a like database and then read it from there and then use it for your processing. The next thing we talk about is Parquet partitioning. So partitioning optimizes the reads by storing them in a hierarchy. So if you look at this, if you partition by year and by month, so it, within the file directory, the year 2018 gets split into each month, and within each month there's multiple Parquet files. So we partition it based on the columns that we specify, and you can also have a partitioning hierarchy. So that's you could also do it based on state and city, country and state. So all those things are doable, and you can partition based on any of those fields. Data frames can be saved as persistent tables and into a Hive metastore. So you can actually save the data frame like df dot create or replace table or save as table. So if you use the df dot save as table command, that will save it as a persistent table on Hive metastore. And yeah, if you don't have Hive setup, Spark will create a local Hive metastore using Derby. Derby is a database that's RDBMS. Persistent tables, and this is what is used by Hive in the backend. Persistent tables have several optimization benefits. So if you have a persistent table, that is, you write this into a persistent table, you can have partitioning, you can have statistics of metadata, you can have them bucketed. As an example, like if you have a flight data set like this, lot of like it has like departure time, arrival time, and like elapsed time. So this is the arrival time, this is the departure time, and any delays within departure or arrival, and total elapsed time and the total distance. So all this is for one leg of a flight that starts from ATL and goes to LGA, Atlanta to LaGuardia. So that would be shown in this one JSON row. So now, if you have a lot of queries about departure delays, and you have them around the originating column, that is the source column. Okay, if you want to do it based on the source column, so this could make a good partitioning column. So you can actually partition based on the SRC. So how would you partition it? So you write tf.write.format Parquet, use the partition by, and use the column that you need to partition it by. So the SRC goes here, and you give the option as path. So you specify the path where it gets stored, and then you save as table. So in the Hive table, it gets stored as a flights Hive table. So the data that gets read from this JSON format from the file gets stored in a Parquet file under this location, and we partition that Parquet file by SRC, and we store that as a Hive table under the name flights. When you actually go into Hadoop FS and type in the full directory name, and then you would get all these split by the SRC field. So the SRC ATL goes into this location, SRT Boston goes into this location, CLT goes into this location, and so on. Here we can see that within SRC, one of them, so if you go into, like here, you give slash SRC equal to DEN, so the Hadoop FSLS command, that would mean it will show the two parts within the partition. So within the partition, there are two buckets. It shows those two here. Okay. Next one is partitioning, pruning, and predicate pushdown. So this is used to performance optimization that limits the number of files and partitions that Spark reads while querying. So after partitioning the data, queries that match certain partition filter criteria improve performance by allowing Spark to only read a subset of directories and files. So instead of reading all the files, because we can prune the partitions, and you can use the var clause or the predicate pushdown. So Spark is able to actually read only a few partitions. So it knows which partitions it has to read, and because of which it reads only a subset of the directory and files. It does not always have to read everything. So when the partition filters are present, that is, you want to inquire by the SRC equal to den. So here we have a filter and another filter here. So because we have these two checkpoints, we know we just have to read the partition files that are under DEN. We don't have to read any of the other partitions. For this, for departure delay, there is no partition, so it has to read everything within the DEN partition. So those are these two files. It has to read both these files and all the records inside those. But it doesn't have to read any of the other files. So it doesn't have to read any of these. It doesn't have to read any of these, any of the files after these. So that is an optimization that when you filter much early on, if you know you have to filter, apply the filter much early on. That would probably help. But sometimes, like Spark is able to write code such that even if you do the filter later, if Spark knows that you need to filter it, it might be able to do that by itself. But as a coder, I think it's the right thing to do by filtering it as early as possible so that you pass fewer records through the pipeline. After partitioning the data, the queries that match the certain partition criteria, only those get read. So when the partition filters are present, the catalyst optimizer, so this pushes down the partition filter. So we get only the partition filter. So this is done with the catalyst optimizer. The scan reads only the directories that match the partition files, thus reducing the disk IO. For example, the following query reads only the Denmark part, DEN partition, sorry, not Denmark, to get the average departure delay for the flights coming out from Denver. You can do this in Spark SQL as well. You provide a where condition with all those conditions. You pick it up from the flights table that we defined in under Hive. You do a group by source and destination, similar to what we do here. Group by, and then at the end we calculate the average departure delay. So that happens here. And here within the select command, we have like source, group by, source, destination, and average. So these three commands, these three are the only columns that are displayed here. And we order by SRC, which is different from here. Here we order by descending of average departure delay. Here we don't do that. I don't know what is the reason for doing it differently, but we don't have to. When you go and check the physical plan, so if you do an explain, it will give you the physical plan that Spark uses. You can do that. Here you can see that the partition filter push down, that is, this filter is pushed down into the partition Parquet file scan. So this means the number of files read, data scanned is reduced a lot. So where you have to see this is when you do the query dot explain, you can do the same thing for the SQL query as well. If you do the explain, it shows the physical plan that it does. So it does a order by descending nulls last, and it does the output here. If you look at this, it does a hash aggregate based on source and destination. It does an average function. The output is just three fields. It uses the exchange hash partitioning. It does a hash aggregate again, source and destination. The functions it does are partial average, and then output is the source, destination, and then sum of this and the count of this. So it uses this to calculate the actual average. So it does the sum of one field and then count of the same field. So now average is nothing but the sum of all the numbers divided by the count. So to do that, it does this hash aggregate. And if you look at this, it does a project, and then it projects these three, and it filters is not null, delay greater than 1. And before all that, to remove non DEN files, so what it does is here it goes into this is the first step. So if you look at this, very much before anything starts, so it looks at just the DEN file, and it sees that the partition count is 1. Only one partition needs to get read. Within the partition there are 2 files, but only one partition gets read. And then this gets read by this. Then there is another filter here, and then this gets to a partial calculation of average, and then the full calculation of average, and then this gets the output out. So if you look at that, it starts with pulling the right partition alone. So here itself, it makes sure that only the limited amount of data is read. The physical plan is read from bottom up. But when you look at the DAG, if you look at the hue to check the DAG, so you'll see that you'll read it from top to bottom. Exchange is actually a shuffle that occurred between the stages. So here, if you look at this, so it started here. It started with the scan Parquet default flights. It reads 23,410, and then it took a total of 150 milliseconds. And then it filtered the number of output rows because there is a greater than 1 option. It filtered out to 800, 373, and then it projects it over. It does a hash aggregate. It takes 172 milliseconds for that, and then it produces 24 rows as output. And then it does an exchange, and then that is a 1 KB of exchange it does. And then there's a hash aggregate which calculates the average, and then take our ordered and project it. So here is where it gets ordered again. So if you look at this, it took a total of 1 second, and then there are 7 jobs that got submitted. 1, 2, 3, 4, 5, 6, 7. Partitioning tips. How do you use partitioning? Partitioning columns should be frequently used in queries for filtering. So whenever you want to partition, think about, are there any filtering that you use? Do you look at it by year? Do you look it up by state? So typically, do we have state-wise queries that are on year-wise? Do we do it by quarters? So think about that when you determine what your partitions should be. And you cannot have an ID column for a partitioning. It should typically have small range of values. So if a list of states in a country, that probably is acceptable. Say age is probably acceptable, age range even better. But somebody's last name is probably not acceptable for the partition columns. Rather, if you have the first letter of their last name, that might be better. You might have only 26 partitions, but you might have very few names starting in Z or V, while there are too many names starting in A or S. So that might cause a skew. So you'll have to think about that as well. So not only what you filter by, but also do you have a proper range of values there, and are there close to equal, so that you don't cause too many skews as well. You want to avoid too many small files, so you don't want to have small file problem. So in Hadoop, small file problem is a problem we like to avoid. We don't want to have too many small files that create metadata in name nodes. Rather, we want to have like a GB sized file or a 500 MB sized file. So that's a typical goal we have. That makes the scan less efficient. If we have small files, it makes the scan less efficient, and we have too much parallelism. So parallelism is good, but too much parallelism is probably something we want to avoid. You also don't want to have too few large files. That means too less parallelism. So you want to have a balance between those two. So this is something we have to consider, a difference between coalesce and repartition. So before or when writing a data frame, you can use a data frame to coalesce and give a number of partitions or number of like partitions you want to coalesce it to. This helps reduce the number of partitions in a data frame. Without shuffling it, you can do this. So one option is to actually do coalesce. Say if you do coalesce of 10, and you currently your data frame has 20 nodes, 20 partitions. So if you want to reduce the partitions from 20 to 10, then if you use coalesce, then it would like combine 2 into 1, so it will combine 20 of them into 10 of them. So it wouldn't actually shuffle the data between them, make them equal in size or anything like that. But if you actually use a repartition, the data does get reshuffled, and then you might have pretty similar number of rows in all the partitions. And you can use repartition to actually decrease the number of partitions or increase the number of partitions. So if you want to increase from 10 to 20, coalesce is not an option, but you can use repartition for it. But when you go from 20 to 10, you could use either coalesce or repartition. Typically, if you don't want the data to be shuffled over, which is a very expensive operation in Spark, you would rather use coalesce. So here is an example where they use repartition, and here they repartition by partition by SRC. And repartition helps achieve a very even load balancing, because it does almost pretty close to equal number of rows per partition. Bucketing. This is another interesting topic. Bucketing is often confused with partitioning, or maybe an addendum to partitioning that we also use so that we parallelize the work. Bucketing is another data organization technique. You group the data with same bucket value across a fixed number of buckets. So here the key is that we provide a fixed number of buckets when we actually set up the buckets. When we partition based on a column. Say if we do a partition based on a state column, if there are 20 states, then your data gets partitioned into 20 partitions. If you actually have 50 states, your data gets partitioned by 50 columns. But in buckets, you can actually specify the number of buckets, and the buckets need not have 20 different values for 20 buckets. It can have 200 different values, and if you specify move these 200 into 20 buckets, then your system will automatically move ranges into one bucket, another range into another bucket, and create 20 buckets. This is another way to actually improve performance. Like you can also avoid shuffles. With wide transformation shuffles, data sent across the network to other nodes. So when you do a shuffle, what happens is data is actually sent between one node to another node. So you actually have a network data move, and then in the new node, it's actually written to the disk. So you're actually causing network data and disk IO. And making a shuffle is a very costly operation. It should be avoided as much as possible. So here, if you look at this df by group by carrier dot count. So if we do a df dot group by carrier dot count, if the data set is bucketed by carrier, then the shuffle would be avoided. So if you do this, that means we already have a like here what happens is we do a shuffle. So if when we want to group by carrier, which is like A, UL and DL, here because this bucket has A, UL and DL, it has to get shuffled over. All the A's have to go here, all the UA's have to go to the last bucket, and the DL has to go to the middle bucket, and that has to happen across all these buckets. If we already had bucketed and we had it bucketed by the carrier, then we would already have these as A's separately, DL separately, and UA separately. You don't have to really repartition it. So what's the difference between bucketing and partition? This is a common interview question. Partitioning creates a directory for each partition. So in the physical location, you get a different directory for each partition, but bucket distributes the data across a fixed number of buckets, and it uses a hash value on the bucket rather than like unique values. So if it can have like you can use an ID column or a name column to actually use a bucket, which has a lot of cardinality. But partitions, you typically use something which is low cardinality, and each separate value gets a separate folder physical structure for it. In bucket, there's no physical structure. It's just the way how we can process the data. Tables can be bucketed on more than one value, and bucketing can be used with or without partitioning. So you can use a bucket, but you need not really have the table to be partitioned. As an example, if you look at this, like you want to persist the flight data frame, and you want to use Parquet files partitioned by the src column here, but you also want to bucket by the DST and carrier columns, and you want to use 4 buckets for it. So you want to use 4 buckets, and you have 2 columns you want to bucket it by. So that's how you use this logic here. You also want to sort by ID, um, and that will mean that you'll sort by ID. You'll also have a separate file by SRC. You'll have a separate bucket for each destination and carrier. So you have multiple ways by which you get this. So with all this, you make sure that your whole data set is split by multiple ways and sorted by ID, like split by source. It's also bucketed by destination and carrier. Uh, so if you look at the resulting directory structure, it looks the same as before. So you won't see any physical changes because you added bucket by. Um, but if you do an analyze table, that's when you will see the difference. So here, if you look at this and we do a df2.filter, and then we get all the DEN source and we do the same query. And then you do an explain here. What we see here is, let's read from the bottom this time. So what it says is file scan Parquet default dot flight. It does a carrier. It does a pushed schema. That is, it checks it's not null and departure delay, and it checks the greater than departure delay 1.0. And then it does a filter. It does a project. It does two hash aggregates like earlier. One is a partial average and other is a full average. And it doesn't specify what partition. Okay, here it specifies what partition it is. And then the partition count. So if you look at the DAG, we can see the difference very clearly. So here we see that there's a scan of the Parquet file, 23,000 records, and then there's a filter that's 8,000 records. There's a project that takes 96 milliseconds and it outputs 28 records. And then there's a hash aggregate, and then we get a take order in project. Here, if you look at that, partitioning should only be used with columns that have a limited number of values. So if you have a limited number of values, partitioning might work. Bucketing works when you have number of unique values is large. Columns, which are often used in queries and provide high selectivity, are good choices for bucketing. So if you know that it's going to be part of like the where condition, the order condition, the group by condition, so think about it. And if it has a very high cardinality, bucketing makes sense for it. Spark tables that are bucketed store metadata about how they are bucketed and sorted. So that helps optimize the queries on the bucketed values. Next, we look at data modeling. How do you partition? How do you do a filter push down? How do you data model in a Spark table? So partitioning and row key design. So with the MapR database, table is automatically partitioned into tablets and across a cluster by key range. Okay, let's look at Spark Web UI and SQL tips. So when you use the SQL tab, you can check the amount of time for each stage. You can check the partition filters, projection, and filter pushdown occurring. Shuffles between stages, that is exchange, and the amount of data shuffled. You can check all that. If joins or aggregations are shuffling a lot of data, consider bucketing. You can set the number of partitions to use when shuffling with this option, shuffle.sql.sharp partitions option. If you use the join algorithm, broadcast join can be used when the one table is small. Sort merge join should be used for large tables. You can broadcast hint to guide Spark to a broadcast join in a join. For faster joins with larger tables, use sort merge join algorithm. You can bucket to pre-sort and group tables. This will avoid shuffling in the sort merge. Use the Spark SQL analyze table, compute statistics. So if you use that, you'll understand what plan it's using. Stages tab. So if you look at the SQL UI and then go to stages tab, you can see how the stages are. You can see which tasks are taking longer. You can see any kill tasks. You can see if your process time is not balanced. You can check the shuffle read size and see if it's not balanced. If you check the partitions or tasks and you see that they're not balanced, then you can consider repartitioning it under partitioning. Okay. And there's a storage tab. Here you can see caching data sets. If you want to cache certain data sets, that might make the execution faster. You can look at the storage tab to see if important data sets are fitting into memory. Executors tab, you can use the executors tab to confirm if your application has the amount of resources needed. So if you want to check the shuffle read memory write columns, read write shuffle read write columns shows the size of data transferred between stages. Storage memory column shows the concurrent used or available memory. Task time column shows the task time garbage collection. And here's all the references this person is listed. That's it. Thank you so much.